So let's take a look at this problem here. Since we were working with area last time and I gave you some formulas for basic shapes, then we probably needed to use a little bit of critical thinking skills to see what we needed to do here, right? First thing we should always do is read the instructions. So I'm going to go ahead and read these aloud. Find the area of the following figure with the indicated dimensions. Round the answer to the nearest hundredth, right? So if we are trying to find the area of this thing, we have to think about, okay, Mr. Aguilar only gave me formulas for certain kinds of shapes, right? We looked at triangles, rectangles, squares, parallelograms, trapezoids, okay? So what we need to do here is say, okay, if that is all I have to work with, can I break this figure up into a couple of those shapes, right? And so you might have realized that this part, even though it looks like a square, the dimensions are not the same on each side, right? So this part is a rectangle because the length and the width are not the same. Okay. And then this part over here is a triangle. So what I could do is combine my formulas by finding the area of the rectangle. I'll put rectangle here, which should just be the length times the width of this thing that I've coded in purple, right? Okay, so that just means I need to multiply 7.42 times 8.01, and I'll be able to get that interior surface, the area of that rectangle. Okay. And I said, okay, well, for now, when we work with decimals, I would say go ahead and use your calculator unless you want to practice decimal multiplication, right? So if I threw this in the calculator, 7.42 times 8.01 should be 59. I'm getting 4342. I'm going to keep all of those decimal places for now. Okay. So that should make a little bit of sense, since I sort of know that, if I forgot, or I just ignored the decimals right here, 7 times 8 is about what? 8 times 8 is 64. So this would be 7 times 8. 50 something. Right. Let me go ahead. 49, 56, right? Yeah. So I had to go there in my head and say, okay, well, I know 7 times 7 is 49. Let me add another 7 in there, and that'll be 56, right? So if this is a little bit more than 7, and this is a little bit more than 8, then we can sort of expect this to be a little bit more than 56, which it is, right? 59.4342. And that's one like intuition that you can use to see if you're on the right track, if those numbers are multiplying to about the right number. Now, if I had, misplaced the decimal, and let's say that I put the decimal here and said 594 or 5.9, blah, blah, blah. Well, then 7 times 8 should not be 5, right? So we've misplaced the decimal there. That sort of gives you an indication that you've done something wrong. In any case, is everybody okay with finding the area of the rectangle? Okay. Well, then we have to find the area of the triangle. And we said that the area of the triangle should be equal to the base of the triangle times the height of the triangle divided by 2. Okay, and remember, we're writing division as sort of a fraction. So you can always interpret a fraction as a division problem. But here it looks like they only give us the height of the triangle, which is indicated by this dashed line. That dashed line is the height. So the triangle is sort of flipped onto its side, but that dashed line on the triangle will always give you the height. So if we know that the height of the triangle is 6.46, then we need the base of the triangle. And I mentioned that the base of the triangle is usually the one that's perpendicular to the height. So really it's this side over here of that triangle. Well, they didn't give us a number there, right? But based on our properties of our rectangle, where the rectangle has this side is equal to this side, we can infer that the base of the triangle should be this 7.42. Does anybody have any questions about that? Right, so if you needed to, let me go ahead and erase some of this jazz that I put all around my shape. If you need to, just to make it a little bit easier on you to find out what goes where, what numbers I need on which sides, remember that for the rectangle, this side is equal to this side. So we can go ahead and write 8.01 there if we needed to. This side is equal to this other side. So we could put 7.42 on this side. And then we have everything that we need, right? We have this side of the triangle, which is the base, and this height of the triangle. So we can multiply these together, and we can do this as a two-step process, right? Because we have to multiply first 6.46 times 7.42. And again, 6 times 7 is about, what should that be? 42. So since this is like almost 6.5, like 6 and some change, and this one is almost 7.5, so like 7 and some change, we should have something a little bit higher than 42. Right, that's a little trick that we can use to see what our answer is going to be and if we're on the right track. So I could throw this into the calculator, 6.46 times 7.42, and I get 47.9332 for that. Okay, so that is my area of the triangular part. And remember, we had this area of the rectangular part over here. Well, if we want the total area of this whole figure, we need to add or combine all of that together. So what we should do is just take those numbers and add them. So 59.4342, and then 47.9332. We'll add that up, and I won't bother to use my calculator here since adding decimals is pretty straightforward. This should be 4, 7, 6. This should be 13. So I'm going to bring the 1 up, bring the decimal down, and 17. And then we have 10. So this is our exact answer based on the multiplication and the addition that we've done. Okay, but if this is exact, we need to be very careful about what the answer, what this is asking of us, right? And this last sentence over here says round the answer to the nearest 100th place. Okay, so we'll go tenths. 100th place is right here, the second place value after the decimal. So if we look at the neighbor to the right, and if that neighbor is a 5 or more, then I can bump up our place value of interest. So that means I should write my answer as 107.37, and then I can ignore all the other place values. So this is what I should be entering into the little answer box.
Quick question.
Sure.
So if the triangle is the base times the height divided, you didn't do the divided by 2.
Oh, yeah, no, you're right. I totally messed up, Ben. You're absolutely right. Then thank you for catching that. Then this is all wrong. And it's a good thing that we caught that, right? Teamwork makes the dream work. It's a good thing we caught that before I entered this answer. Because sometimes it's hard to find out, where you went wrong, but you're absolutely right. Thank you for catching that. So what we needed to do is take this number, which was the base times the height. I was getting ahead of myself. And we still need to divide it by 2. Okay, so 4, 7. And again, with these decimal numbers, the bigger fish that we're trying to fry here is we're trying to get the area, right? So for these decimal calculations, I would just use your calculator, okay? Let's just go ahead and divide this by 2, see what we get there. Okay, so let me grab my calculator, divide that by 2, and I get 23.9666. Okay. All right, so this is the area of the triangle. And that makes sense actually, because the triangle, if you just eyeball it, it should be roughly half. It should be smaller than the area of the rectangle. It looks like a smaller shape. It takes up less space. So now we can go ahead and add the area. So the 59, 43, 42 plus the 23.9666. And I'll just throw this in the calculator as well. So plus 59.4342. And I'm getting 83.4008. Still need to round this to the nearest hundredth. So the 100th place is going to be the second place value here. But since this is a 0, we don't have enough, right? It needs to be 5 or more in order to bump this up. So since we don't have that 5 or more, we're going to go ahead and just ignore everything else and just call this 83.40. And that should be our answer. And of course, since the measurements were in feet, our area is measured in squared feet. So that little 2 here means squared. Okay, so let's go ahead and type this in and see if it works. See if I didn't make some other mistake in the background. Okay, so 83.04, sorry, 40, there we go. Hit submit answer, and we're good, right? If we follow the process, if we don't forget to divide the area of the triangle by 2 when we do that multiplication, we should be on the right track. Okay. Does anybody have any questions about that one? Notice that this problem took a lot of working out. It took a lot of scratch work before we could actually get to the right answer. So you want to make sure that you organize the math that you're doing and that you're not bunching up all of the work, right? I did the work for finding the area of the rectangle to the left side. I took the space on the right side to look at the area of the triangle. And then I had some space here in the bottom right to add those areas together. And I labeled some things, right? So that I wouldn't lose track of what these numbers meant and where they went or what they corresponded to. So just make sure that you come up with a system so that on your sheet of paper, that's your workspace. You want to have that workspace organized so that you know what you're doing, okay? This isn't the kind of thing where, if you're just doing some quick math and you grab the back of an envelope and you're just scratching some work on the side of the envelope, or you just, grabbing a sheet of paper and just writing it willy-nilly. The more organized you are when you work these out, the more it will make sense and you'll be able to commit this stuff to your long-term memory. Okay. Well, let's look at another one of these to see if we can find that problem that has fractions. And if we can't find it, that's okay. We still have more time to work on this homework, but also we're going to be working on fractions today. So let's see.
Good, because that's where I completed this one, but I started on the other one. and I got stuck on a problem that wanted me to convert my answer into a fraction. And I don't know what I'm doing.
No, not seeing any fractions here. Okay,
I
Well,
think it was in the certified one, like the certified one.
I wonder, I don't know that the certified lets me skip.
I don't remember any fractions being
In the area, I'm thinking,
on the area. Yeah.
yeah, I'm thinking that in the area there probably wasn't fractions. It must have been in one of the other homeworks. Okay, well, let's do this. Let's go ahead and get on with fractions so that we can learn that material, so that wherever you was confronted by the fraction, that you will know how to handle it next time you hit that problem.
That answer was 625.
Yeah, it was 625. I did 5 times. No, I think I did 5 times 5 in my head for some reason.
Oh, okay.
Yeah, I was thinking of something else while I was talking. So 625 should have been the answer to that, the area of that square. Let's go ahead and let me share my screen with you guys so we can get this lecture on the road. Let's go to my document camera. Boom. Okay. Now, in that problem that you saw with fractions, wherever it was it adding fractions or was it multiplying fractions? I'm just curious.
It was dividing. I just didn't know what to.
Okay.
The problem that I came across that tripped me up was -36/7 divided by 63/5.
That one, yeah, division. It was a fraction.
Because I was like,
Can you repeat that to me one more time?
yeah, -36/7
Mhm.
Divided by 63/5.
It was just a straight up division problem with fractions.
Yeah.
Huh.
That's what I was talking about.
Yeah, I wonder what section that
And
was
then
in.
the answer wanted it to be a fraction. So
Yeah.
I was like,
Do you remember what section
Yeah,
this
and-
was?
And yeah, I'm sorry.
Oh,
And I,
go ahead. Go ahead.
oh, I'm sorry. Okay, and I got it, and I got a decimal. When I was trying to put the decimal in the fraction, it said it wouldn't be needed, so I didn't know what to do.
Yeah, if you're dividing fractions like this and it doesn't
Yeah.
say that you can use a decimal answer, then you're not allowed to use decimal answers. Your answer will be in the form of a fraction. But you guys don't happen to remember what section of the homework it was in, right?
It was like the second, I think it was like the second or third question in the certify.
Second or third, certified. Okay.
It has to be multiplication and division, I think.
Yeah, that one.
Oh, okay. So it was probably an 8.4.
Yeah.
Yeah.
Okay, I'll go and check that out. And if I see any fraction problems there, I'll take that out because we're going to have a whole section on multiplying and dividing fractions tomorrow. Today, we're going to do adding and subtracting fractions.
So that wasn't supposed to be in there or something, or?
No, those questions, I was under the understanding that those questions in the certify and in the practice should have only been whole numbers because that's all we've been working with. But I'll go in there and I'll remove the ones that have fractions. Okay. So let's go ahead and what we're going to be doing today is looking at section 2.6 because that section is on adding and subtracting fractions. But we have to do a little bit of work here to sort of understand what a fraction is. And we've talked about them a little bit, but I'll go ahead and remind us how fractions work. Okay, so fractions are essentially telling us something about the parts of some whole. What do I mean by that? If you have a whole pizza, right, and you cut it up into smaller sections, essentially you've divided it up into smaller pieces. you could talk about, getting a whole, one whole pepperoni pizza. But how many pieces is a pepperoni pizza usually cut up into? Does anybody know how many
8.
slices?
8.
Yeah, 8 slices. If I said, I will trade you 1 slice for 1 pepperoni pizza, would that be a fair trade?
No,
Why not?
because it's 1 out of 8 slices.
But if I give you 1 slice, why is that not the same as 1 pizza? It's 1 and 1, right?
Because the pizza is 8.
Because the pizza is 8 of those slices. So we're actually talking about different kinds of objects, right? That have different size or different value. So a fraction, they tell you something about an object being divided into smaller parts. Okay, so if we're talking about that pizza, I could say that for that pizza, 1 whole pizza would be 1 of these circles. Okay, this is 1 whole pizza. But typically, we divide that pizza into 8 slices. So we can take that same shape, which relatively is the same size, right? And just cut it up into smaller portions. We'll cut it in half. We'll cut it in half again. We'll cut those quarters into halves. And then we should get 8 slices that are roughly the same size. So if I needed to express, I have 1 whole pizza here, that's the same thing as having 8 slices. There's a conversion factor here. You're working with the same denomination or the same kind of currency, right? Like if I were to give a person, I don't know if you guys are familiar with the exchange rate for Japanese yen versus the US dollar, but if I gave somebody in Japan $1 and they gave me a yen, that would be a 1-to-1 trade, $1 for 1 yen. But 1 yen is only worth about 1 cent, right? I would need 100 yen in order for that to be a fair trade. In the same way that with this pizza trading example, I would need 8 slices to trade for a whole pizza. Well, the way we would express this fraction would be each of these slices is actually worth 1/8. So we would say 1/8. And that's usually how we communicate fractions. Whatever the denominator is, that's sort of the name of the fraction, and we put a th at the end of it. So if we have a fraction, let's call it n/d. Okay. Now I'm using n and d as variables just for placeholders, because these could be whatever numbers, whatever whole numbers that we want. Then the n, the numerator, is what we call the top number. The d, the denominator, is what we call the bottom number. The denominator tells you how many slices in total make up the whole thing, the whole object that you're talking about, whether it's a pizza, a bar of chocolate, a dollar bill, which you could break up into change if you wanted to, right? So the denominator tells you how many total slices our object was cut up into or divided up into. Okay, and the numerator tells you how many, that's many smaller pieces we have of that object. Okay. I'm gonna give you guys some time to write that down if you need it. You guys good on this page?
No, not yet, almost.
Okay. Okay, the first thing that we're going to do here in a second is adding and subtracting fractions with the same denominator. Okay, because this should be pretty straightforward. Adding and subtracting fractions with the same denominator. Okay, I'm gonna keep going. Let's look at an example here. If we needed to add, let's say, 1/2 plus 1/2. Can anybody just venture a guess on what they think? You know, when we add these two fractions up, what should we get?
1 whole.
Yeah, we should get 1 whole, or just the whole number 1. That should make sense if you can interpret 1/2 correctly, right? Like if we had 1/2 of a pizza and we had 1/2 of another pizza, we could say that we have 1 whole pizza, right? That makes intuitive sense. Okay. But if we did that, I mean, the math here sort of looks weird, right? Because it doesn't seem like we did anything with the 1s here. And it doesn't seem like we did anything with the 2s here. Right?
Wouldn't that be 2/4?
No, it wouldn't. But that's a good mistake to make. Okay. So a lot of students think that if you have 1/2 plus 1/2, 1/2 plus 1/2, that you should add the numbers on top and add the numbers on the bottom. That would be 2/4, right? So this is actually the wrong thing to do. So you can't just add the numerators and add the denominators. Because if we think about now this fraction here, and we think about this as a decimal, right? We could represent this as a decimal. We could go ahead and say, okay, if we wanted to write this as a decimal, this would be cowboy sleeps inside, the horse sleeps outside. We can do long division here. 4 does not go into 2, so we're going to need another decimal there. 0 there. 4 goes into 20 5 times, and we get 20. So we get 0.5. So what you're telling me is that if we were to do this, 1/2 plus 1/2 is equal to 0.5. Since that is an equivalent decimal representation, right? This is equal to this. But 1/2 is 0.5. And so if I added 1/2 or 0.5, 50 cents, $0.50, to another $0.50, and then if I got 2/4, which turns out to be $0.50 as well, does that make sense? If I have 50 cents plus 50 cents, I get 50 cents?
No.
No. So that's the reason why we can't just willy-nilly add the numerators and add the denominators, because the math doesn't seem to work out. Okay. So this process won't work here. So you need to make sure, and I know it's super tempting for most students to just add straight across when we're adding fractions, but we don't want to do that. Okay. So let me give you the process for adding fractions with common denominators. So adding fractions, subtracting with common denominators. That is the same denominator. You are going to add the numerators or subtract them if that's the problem, if it's a subtraction problem. And you want to keep the common denominator. Okay. And I think that this is really nice actually, because if we think about this in a linguistic sense, that is when we're talking about 1/2 plus 1/2, to just stick with this example, 1/2 plus 1/2, right? You could think about this like the denominator just tells you the name of the object. Okay, so if I have 1/2 plus 1/2, it's like if I went to the store and I said I have 1 apple and then I received another apple. How many apples do I have? Well, I have 2 apples, right? So if I have 2 objects that are of the same denomination, they're the same kind of object, then I should just say, okay, I had 1/2 plus another half. So I should have 2 halves. And then we can figure out, okay, well, maybe the 2 halves would be easier or simplified and call that 1 whole. We'll figure out how to do that here in a second. But the process for adding and subtracting fractions with a common denominator is going to be add or subtract the numerators, whatever the problem says, and then keep the common denominator. We'll figure out how to simplify those fractions in a bit. Okay, let's look at some more examples. Okay, let's say I had 4/15 plus 6/15. Okay, now you could just memorize the rule here for sure, but I don't think that's as enriching as thinking about this linguistically, as thinking about what is the denomination, the name of the object that we're talking about. Remember, the denominator gives that fraction its name. So here you could think about this or interpret this problem as having 4/15 plus 6/15. Okay, and if we think about it that way, if I have 4/15 plus 6/15, how many 15ths should I have?
10,
I should have how many?
10.
10. Right, because we're just taking the 4 and the 6, the numerator, right? We're taking the stuff on the top and adding them. So it's like we just take the numerators, add those together. 4 plus 6 is 10. So we should have 10, and then we're going to keep that common denominator. And for now, just until we get the hang of this, I'm not going to worry about simplifying. I know that we probably have some ideas of how we can simplify, but I just want to make sure we get this rule down correctly. And then we'll simplify some fractions in a bit. Is everybody okay with that?
Fine with me.
Let's look at another example. 1/11 plus 5/11 plus 3/11. Okay. And again, you could interpret this linguistically. We're talking about some denomination of objects. You could think of a pizza that's been cut up into 11 even slices, which would be strange. It'd be a strange slicing pattern of the pizza, but you could do it. But in any case, you could think about having 1/11 plus 5/11 plus 3/11. So how many 11ths should I have in total here?
Wouldn't it be 9/11?
Yeah, because 1 plus 5 is 6, plus another 3 would be 9. So it would be 9/11, 9/11ths. Does that make sense?
Yes.
Okay. Now you don't want to necessarily, like, maybe in your head, you could think of this as like 1/11, 5/11, 3/11, and add those objects up. But typically we won't write that down. You don't have to. So let's look at a similar problem, right? 3/12 plus 5/12. And without doing that linguistic thing on paper, at least, what should this be when we add them together?
8/12.
Yeah, 8/12. Because we're adding these, and then we're keeping that common denominator. One ninth plus 4/9 plus 3/9 should be what?
7/9.
7/9.
No, that's 8.
8/9.
My bad. That's 7. That's an 8.
Oh, that's 8. Okay, yeah.
There we go. We just miscounted there, right? That was the only issue. But we're good. We caught it. 1 plus 4 is 5, plus another 3 should be the 8. Does anybody have any questions about these?
No.
Does that feel a little clearer
Yeah.
on how to add those fractions together? Okay. Well, there's one thing that we need to think about for a couple of these problems. So for this fraction here and for this fraction here,
Yeah, it can be reduced.
it can be what you might have heard in the past is reduced. And, I usually say the word reduced too. But I think reduced, sometimes we think that the value should be smaller. This is hard to sort of describe, but it leads us to the next topic, that some fractions look different. They look like they're different sizes, but they actually have the same value. Okay. For instance, in one of these previous examples that we looked at, I said that 2/4 is the same value as 0.5, is the same value as 1/2. 1/2 is also 0.5. But 2/4 doesn't look like 1/2, right? This looks like it has bigger numbers. And yet, even though that clearly looks like it has bigger numbers, it has the same value as this other fraction that has smaller numbers. So what's going on there? That's sort of what we need to think about so that we can reduce or simplify our fractions. Okay. So let me go ahead and talk about equivalent fractions, because we will have to simplify or reduce our fraction problems whenever we get to the end of them. So equivalent fractions. because fractions are division problems, some fractions may look different, but have the same decimal value. So you could think of them as being worth the same amount. Okay, so if I were to look at, let's say, 500 over 1,000, it turns out that that is equal to, let's go with 25 over 50. And that is also equal to 1/2. Okay, this is what we would call equivalent fractions. So and there's two ways that we can sort of see that they're equivalent fractions. I think the first way is just sort of eyeballing it. Remember, the denominator is the whole number of parts that something has been divided up into. And the number on top, the numerator, tells you how many smaller pieces you have. Well, if you look at the number 500 and 1,000, 1,000 looks like it's 2 times the size of 500, right? 500 times 2 would give you 1,000. So we could say in some comparison, if I had one 500 on the top and I had 1,000 on the bottom, that's like I'm having 2 500s on the bottom. Okay, what do I mean by that? Well, if we just take a look at 500 over 1,000, I could say, well, let's leave the 500 alone and let's change or convert my 1,000 and rewrite it as 2 times 500. Okay.
So does that mean it makes it like a whole, the same like a half would be?
What do you mean? What are we
So
talking
like,
about?
you know how you have the 500 over 1,000, then you have 25 over 50, and then you have like the 1 over 2. I
Mhm.
mean, is it gonna be like, when you first start doing it where it's like a whole? Because, 2 times 500 is 1,000, like a whole, like one whole.
Oh, it's more like this. Like the 1,000 is made up of 2 times 500, right?
Okay.
And on the top, the 500, you could think about it like 500 times 1. Right? Since 1 times 500 is still 500. And what you really need to think about here is like fractions are division problems. So if I have a number on top that is the same as the number on the bottom, then I can just divide those numbers out. We say that they cancel out, but they cancel out by division. So I could take 500 divided by 500, and what should that be?
0.
Ooh, be careful
Oh, you
there.
said, wait, you said
One.
500 times
Wouldn't it
500?
be 1?
No, he said 500 divided by 500.
Would it be 1?
Yeah, it'd be 1. So if I cross these out and say that they cancel out because they equal 1, well, then I would have a 1 over 2 left over. And you could say times 1, since the 500 divided by the 500 equals 1. But that won't make a difference here. We'll just end up with 1/2. And then we'll say that this fraction, the 500 over 1,000, has been reduced. But it has the same value.
I can also Well, I guess that way it's easier when it's big numbers. Like divide 500 into 1,000.
Yeah, but I think that when students do that, sometimes they end up putting the 2 on the top.
Yeah.
Like, you have to remember that this is 500 divided by 1,000, not 1,000 divided by 500.
Right.
So what I'm showing you is something called factoring. Okay, so let's take another example here, the 25/50. What we could do is factorize 25. And factorizing or factoring is writing larger numbers in terms of multiplying their factors. That is the numbers that multiply to make that number. So what we could do is rewrite our fraction. And you could think about 25, for instance. Can we think of 25 as a couple of numbers multiplied together? What 2 numbers multiply to make 25?
5.
5 times 5.
Yeah.
Right? So instead of writing this as 25, let's write it as 5 times 5. Okay, can we think of some numbers that multiply to make 50?
10 and 5.
Yeah, we can go with 10 and 5. That'll work. So I'm going to put 5 times 10 because it doesn't matter what order we put that in. And if we wanted to like truly factorize this all the way, 5 is what we call a prime number, and I'll discuss that later. But we could write this as 5 times 1, but since we get down to 1, we really can't break up the 5 any further. So I'm going to leave the numerator alone, 5 times 5. Again, that is still 25 if you're following me. But 5 times 10 on the bottom, can the 10 be broken up into something else? Or can we multiply 2 numbers to get 10?
5.
2 times 5.
2 times 5, right? So
2
I'll
times
leave
5.
this first 5 alone. And then the 10 can be broken up into 2 times 5. Okay, so we would say that we've fully factored our numerator and denominator so far. That is, we've broken down the numbers on the top and on the bottom into multiplying smaller numbers until we can't break them down any further. If we have common factors in the numerator and denominator, just like on this example, they will divide out to be 1, right? Like if I have a 5 up here and a 5 down here, a fraction is division. So this is like saying I have a 5 divided by a 5. And since that's going to be 1, those 5s will cancel out. So you can cancel common factors. And if you can cancel all of the common factors, like we have another 5 and a 5 here, and remember that when we cancel, we should have a 1, then this should be 1 over 2.
Oh, here.
Okay. So 25 over 50, when we fully reduce it or simplify it, is equal to 1/2. Okay, so let's do some more addition problems just so that we get back into that frame of mind, adding some fractions with common denominators. And then if we have to reduce at the end, we will do that. And maybe I'll throw some subtraction problems in here too, just so we get some practice there. adding and subtracting. Let's go with 3/9 plus let's go with 8/9 2/9. Okay. What should I get when I add these fractions together?
13/9.
Is it 13/9? So that's
Yeah.
11, 12, 13. Yeah, 13/9. Okay. And now we're just going to do a check to see if we can reduce. Okay, so our check is usually to see, is there a number that we can break up 13 into? Can we factorize it into the product or multiplying two smaller numbers together?
I don't think so.
Yeah, you would just get 1 and 13.
No.
And then 9 could be 3 and 3, right? So if you wanted to, and this is just a check, we could say, okay, this is 13 times 1. And then 9 breaks down into 3 times 3.
Oh,
But
so
since-
where did the one come from?
Which one? This one?
Yeah, where,
Well, tell me this. Isn't it true that 13 is the same thing as 13 times 1?
Yeah.
yes.
Well, then if that is true, then I can always make that substitution.
So he's like saying nothing times whatever is gonna be 13. Only 13 times 1 is 13.
Yeah. Yeah, that's what I'm saying. Like, can you think of two smaller whole numbers that multiply to make 13?
And because there aren't none, that's where the 1 came from.
Yeah,
Okay, thank you.
yeah, you got it. And maybe I should explain that a little bit more. Okay, but for now, we'll just hold that to the side. And then 9, we're just sort of doing a check. And this is sort of, again, another place where it pays to know your times tables and know what whole numbers can multiply to make another larger number. So if we have this larger number 9, and we think about what are the smaller numbers that multiply to make it, well, it has to be 3 times 3. Okay. And the reason why we do this is because we want to be able to cancel common factors on the numerator and denominator. But you'll notice that 13 and 1 are the factors on top, 3 and 3 are the factors on bottom, and there's no common factors across that fraction bar. So since there's no common factors, then we can say that our answer is fine. It's already fully simplified or fully reduced. Let's go with 9/10 minus 7/10 minus 5/10. What should we get when we do this subtraction?
3/10.
Can you walk me through how you got that 3/10?
Well, I just minus the 9 over 9 and 7, and then I had gotten 2, and then 5 minus 2 is 3.
Ooh, but be very careful there.
Okay.
You're right. 9 minus,
It should be -3/10, right?
yeah.
Okay.
So be careful not to flip the order of that subtraction, right? Because automatically you want to take the bigger number and subtract the smaller number so we stay positive. But that's not how the problem is set up, right? So you're right, 9 minus 7 is going to be that 2. But then we need to look at the 2 minus the 5. So if you have $2 in the bank and you spend $5 on your debit card, are they going to say you have positive $3?
No, you're gonna have a negative.
The negative, right? You got to be careful.
They're gonna say you're broke.
Well, what they're going to do is they're going to say that you owe them $3 and then slap a $32 overdraft charge on it.
So
Or you
you
might still
broke.
get declined.
Yeah.
Okay, so that should be -3/10. Okay. And then again, if we wanted to check to see if this simplifies, which I can tell you right now it doesn't, holding the negative sign aside, this is a negative number, so we know that the fraction should be negative. You can just think about this as 3/10. The 3 doesn't break down into anything, right? There's no 2 smaller numbers that multiply to make 3, except for 3 and 1. Okay, so you could just leave it as 3 times 1, or you could leave it just as 3. Doesn't make a difference. We just know that 3 does not break down any further. 10 can be written as 2 times 5. And then we can't break those numbers down any further. Okay, so
Well, can't
essentially,
you also do like 10 times 1?
you could also do 10 times 1, but we want to break it down into smaller factors to see if, when we look at all of our smallest factors, and these are called prime factors, if any of those prime factors can cancel out.
Okay.
Right? If I left it as 10 times 1, it wouldn't be clear necessarily if we could cancel any of those common factors.
Okay.
Okay. So once you've broken these down into their prime factors, and you see that there's no common factors to cancel across the numerator and denominator, then you can say that, okay, I've done all the work that I needed to do. This is fully simplified, so that should be my answer. Okay, let's do another one. I can find where I put my pen. I'll just grab this one. Oh, I'm holding my pen. Okay, let's just do 9/10 minus 7/10. What should that be?
2/10.
Yeah. 2/10.
Which also simplifies.
This one does simplify, right? And that's why I threw this problem in there. Okay, so you might not recognize that it simplifies, but this is why breaking down the numerator and denominator into the prime factors or smaller factors is going to be useful, right? You could say to yourself, let's just go over here with our little thought bubble. 2 cannot be written as 2 smaller numbers multiplied by each other. It would just be 2 times 1. So if you wanted to, you could write the numerator as 2 times 1. That's perfectly fine. But 10 can be broken down into multiplying smaller numbers. What 2 smaller numbers multiply to make 10?
2 times 5.
2 times 5. Here, again, we're checking if we can simplify. Here we do have common factors. Okay, we have a 2 in the numerator and a 2 in the denominator. And if we think about our fraction as a division problem, 2 divided by 2 is 1. So we can cancel those out. What we have left over, the 1/5, is our equivalent simplified fraction. And that's the answer that you would need to put. Because you could put, if we were talking about Hawks and you typed in 2/10, you would probably get a blue warning sign that says, even though your answer is equivalent to the correct answer, it is not fully simplified or reduced. So they want you to simplify every problem that has fractions. So you do the operation, and then you have to
I'm
check,
gonna have to hit you back. I'm in class.
okay?
Alright.
Okay. Maybe we need one more for good measure. Let's go with 10 over 25 plus 5 over 25. Yeah, let's go with that. When I add those fractions together, what should I get?
15 over 25.
Can that be simplified?
Yeah, it can be.
Okay. So walk me through how I would simplify that, or what would it simplify to?
You can do like 3 times 5, because that can go into 15.
3 times 5 works on top.
Yeah.
And then what else on the bottom?
5 times what? 5 times
5.
5.
5 times 5, right?
Mhm.
So we fully simplified fully factorized the numerator and denominator now. So do we have common factors?
Yeah, the 5s.
The 5's over here, and it doesn't really matter which 5's you cancel out. You just need one from the top, one from the bottom. But we can cancel those out. So what we should be left with is 3
3/5.
bits. Okay. Now for now, we're going to continue simplifying fractions as we complete fraction problems, but there's one more flavor of adding and subtracting fractions that's more complicated than having the same denominator, and we need to get to that. Okay, so we're going to have some more examples here in a second, no worries, but we are going to complicate this mix a little bit. And that is adding fractions, adding and subtracting fractions with different denominators. Okay, so imagine I said, I wanted to add 1/4 plus, let's go with 3/8. Now, again, I think that whenever students are confronted with a new thing, sometimes they fall back on their old ways and they just want to add the number straight across. And with fractions, you cannot do that because remember, you have to trade objects with the same exchange rate. We have to be talking about the same thing, apples to apples, oranges to oranges, dollars to dollars, a whole pizza to whole pizza, or slices to slices of the same denomination. Okay.
Would you like add the 1 and 8 and then 3 and 4, kind of like an X?
No,
Okay.
Do you have, I could totally be wrong. Do you have to get the denominator to be the same as the other denominator?
yes,
So then would I have to like multiply, I can multiply 4 by 2. And once again, I could be wrong, but if I do that to the bottom, do I have to do that to the top?
that is the correct process and we'll get there. Okay,
Okay.
but I want to explain why we need to do that. But that's exactly what we need to do. We need to be having a conversation about apples to apples. It can't be apples to oranges. Right now we have 1/4 and 3/8. So we're talking about fourths and eighths, and we need to be talking about the same thing. We need to convert them so that they're the same object, if that makes sense. So let's talk about pizzas, right? If I had 1/4 of a pizza, I could draw a pizza, right? I can just draw a circle and cut it into 4 slices, 4 equal slices. So here's my pizza cut up into 4s, and 1/4 is going to be one of those slices, right? That is 1/4 or 1/4 of my pizza. And I want to add this highlighted portion to a portion of another pizza, but this pizza has been cut up into 8 slices. So let's go ahead and make our 8 even cuts. So cut it into 4s and then cut those up into 2s, and we should get 8 even slices. And so this fraction 3/8, 3/8 says I should have 3 of these slices over here. Okay. Well, clearly the slices are not the same size. But I could make them the same size if I were to go to this pizza over here and chop it up some more, right? So if I made some cuts, let's say I cut this in half like so, and this in half like so. Now I have 8 slices, right? And how many of those 8ths do I have highlighted?
2.
There's 2 8ths, right? So somehow 1/4 is actually the same as 2 8ths, because I have 1/8 here and another 1/8 here, and those are 2 8ths. So now that I'm talking about the same kind of object, I have 2 8ths here, and I have 1, 2, 3 8ths here. And now I'm back to adding fractions that have a common denominator. Okay, so then I can just add those up and say I have 5 8ths. This fraction is fully simplified, so we don't have to worry about that. This is our answer. Okay. So what we can say is that when we compare denominators, we need to find the denominators, or their least common multiple first. Then we can convert to equivalent fractions with a common denominator. Okay. So that being said, you're not going to want to draw pizzas every single time, especially when these fractions become large. Imagine that I had 1/50 plus, let's say 37/100. You wouldn't want to draw a circle and then cut it up into 50 even slices or 100 even slices. It would just be too much time that you're consuming with that problem. You could do it, it would just take forever. Okay. So like it was suggested in class, or just moments ago, right? When we have 1/4 plus 3/8, there's something about the 4 that we know we could do something to the 4 to make it look like 8. And that is, we could multiply that by 2, but somehow in order to get this 2 on top, we also had to multiply 2 on the numerator. And that's how we got 2 8ths plus 3/8, where now we have a common denominator. Okay, so I'm gonna do some more examples with you where we, in the middle of the problem, we'll have to find what the common denominator is, and I'll give you the process for finding the least common multiple, at least one process for finding least common multiple. Anybody still writing this page? Okay, let's look at some example problems. Let's do 1/6 plus 3/10. Okay. Well, the first thing you want to do is make sure that they have common denominators. And if they don't, you need to stop and find the common denominator. So we'll look at these two and say that they are not the same.
Can you ever divide a number into the denominators to get a common denominator, or do you always have to multiply?
You'll only divide if that fraction can be reduced.
Okay,
And sometimes you might have a larger fraction that can be reduced into a common denominator, but that's typically not what you'll see.
okay.
Yeah, usually we'll end up multiplying. But we can see that we have a 6 and a 10 here for the denominator. And instead of drawing pizzas with those even slices, with 6 even slices or 10 even slices, what we can do is list the multiples of 6 and 10. And what I mean by list the multiples is count by that number. Okay, so if we counted by 6s, we say 6 times 1 is 6, times 2 is 12, times 3 is 18, or you can just count by 6s, we get 24, then we should get 30, 36, 42, 48, 54, 60, right? And I'm not sure exactly where to stop, but if I go on for a little ways, and then I go ahead and count by 10s over here, 10, 20, 30, 40, 50, 60, 70, and so on. Eventually, when I run through these lists, I will have some number that is the same in both of my lists, some common multiple. So it looks like 6 doesn't belong in this list, 12 doesn't belong in the 10s list, 30 seems to. So I have 30 there and 30 there. It looks like I also have a 60 here and a 60 here. What I want to do is choose the least common multiple, which will be 30 and 30. Okay, we're going to put that this is the LCM, least common multiple. And that's the denominator that I want to use. Okay, is everybody okay with that?
Yes.
So if that's the denominator that I want to use to talk about a common currency, then I need to write these fractions in terms of something over 30 plus something over 30. Okay, I need those denominators to be the same. So you're going to ask yourself, for this denominator, I had 6. What times 6 gave me 30?
5.
5. So that means I needed to multiply a 5 on the bottom of this fraction to get the 30, which means I have to do the same thing to the top. Okay, so anything you do to the top, you got to do to the bottom. So that would be 5 times 1. This will be 5 over 30. And so that's our new equivalent fraction with a larger denominator. Okay. Over here, I need 10 to change into 30 somehow. What do I need to multiply by 10?
3.
3. So I'll multiply 3 on the bottom here, which means I have to multiply 3 on the top as well. 3 times 3 is 9. There's my equivalent fraction with the new denominator. Okay. Does anybody have any questions there?
No,
Now that I have a common denominator, we're back to the land of adding with common denominators. So we're going to add the numerators, keep the common denominator. You worked so hard to get that common denominator. Let's keep it 14 over 30. And just because we've run out of time, I will say that this reduces to 7/15. And I'll leave it to you to figure out why that is. Okay, but we'll continue talking about fractions, maybe do a little bit more addition and subtraction practice with different denominators beginning next time. And then we'll get into multiplication and division by fractions tomorrow. Okay, so if you have any questions, you can hang back to chat with me for a little bit, but otherwise I will see you tomorrow at 9:10.
Are we gonna have to wait until we finish up tomorrow's homework or tomorrow's lesson before we can finish? Because there were only two things of,
That had multiplying or dividing fractions.
right, there was only multiplying, dividing fractions and, oh, wait. Just like the section, is multiplying and dividing or adding, subtracting fractions on the section? Hold on.
Oh, I've opened up a homework for
Mhm.
adding and subtracting fractions so that you can get practice.
Oh, okay,
And then tomorrow, when we go over multiplying and dividing fractions, I'll open up a homework for that.
okay,
Yeah.
all right, cool, thank you.
You got it.